Today's learning goal is to solve 2D projectile motion problems. Solve two-dimensional projectile motion problems. Okay, so we're going to attempt solving a problem dealing with projectile motion. This is objects moving freely through the air, only under the influence of gravity. So for example, things like cannonballs being fired out of cannons would be projectile motion. A frog jumping through the air, a basketball being thrown at a basketball game. Anywhere where you have an object that's freely moving under the influence of gravity, no like parachute attached to it, no rockets propelling it, no wings providing lift. It's just something that's kind of being thrown and falling through the air. The key here is to remember that we can separate the x motion from the y motion and treat those two motions totally separate from each other. In the x direction, gravity is not acting, so the velocity in the x direction will stay constant. Whatever velocity the object has at the beginning of the problem, that velocity in the x direction will always stay the same. In the y direction, something else is happening. We have gravity acting in the direction, in the y direction. We're going to have constant acceleration motion. So these are the equations that we've used in the past for objects accelerating uniformly. And we should remember that the acceleration due to gravity at the Earth's surface for the Earth in particular is negative 9.8 meters per second squared. So anytime that they don't tell us that we're on another planet and that gravity is different there, we're just going to assume that the acceleration for the falling object is the acceleration due to gravity on the Earth's surface, negative 9.8 meters per second squared. Okay, so let's take a look at a problem. We'll dive right in because we're already familiar with these formulas. Now we're just going to apply them to a little bit more complicated problems where the motion is happening both in the x and the y directions. Take a look. Here we have an example to consider. We have a cannon at the edge of a cliff. The top of the cliff is 50 meters from the water level. So the cannon is at a height of 50 meters above the water. There's a projectile that's fired out of this cannon with an initial velocity of 250 meters per second at 30 degrees above the x direction. So let's draw the x and the y direction. Here's x, and this is y. Okay, so 30 degrees above the x direction. And essentially, this projectile is going to follow some path, something like this. Right, it'll rise, and then it'll fall, and eventually it'll land in the water some distance away from the cliff. Or maybe if it's trying to like hit a pirate ship or something like that over here, right? Hopefully they did their calculations so they can correctly hit the pirate ship. And let's take a look at, we've got some questions involving this problem. So let's look now at the questions. We want to know, what are the x and y components of the initial velocity? How long is the projectile in the air? And how far from the cliff does the projectile land? Okay, so let's do one at a time. We'll start with question number 1. We want to know, what are the x and y components of the velocity? Okay, so the velocity is a vector. We know how to find the x and y components of a vector because we've done these types of problems before when we learned about vectors. So for the x component of the vector, of the velocity vector, let's draw the velocity vector. Has a magnitude of 250 meters per second. And we want to know, how much does it point in the x direction? How much does the vector point in the y direction? Well, this angle here for this problem is 30 degrees. So we know that the opposite side of this triangle that exists here in our imagination underneath the vector is a right triangle. The opposite side is going to be 250 times the sine of the angle. So the y component of the velocity initial, so it would be yi, is equal to 250 times the sine because it's the side opposite of the angle, the sine of 30 degrees, whatever that comes out to. We'll have to plug it in the calculator. And then the adjacent side is going to be the x component, or the adjacent side is the x component. The x component of the initial velocity is going to be 250 now times the cosine of 30 degrees. Cosine because it is the adjacent side to the angle of 30 degrees. Okay, so let's put this in our calculator. $250 times the cosine of 30 degrees comes out to 217 meters per second. And now let's do the sine. 250 sine of 30 comes out to 125 meters per second. So this is the y component of the initial velocity, and this is the x component of the initial velocity. Okay, let's go on to the next problem. Here we have the question, how long is the projectile in the air? So how long is the projectile in the air is going to be determined by gravity. Gravity is the one that decides how long the projectile is in the air. If gravity were very strong, the projectile will come down very quickly. If the gravity was very weak, it would take a long time for the projectile to come back down, right? So gravity is the thing that's determining how long the projectile is in the air. So we're going to be dealing with motion in the y direction, okay, because gravity acts along the y direction. So let's go ahead and write down everything we know about the y direction here in this problem. So we've got that the initial position of the projectile in the y direction is going to be 50 meters. That's the height above the water where the projectile begins its flight. Next, what about the final position of the projectile? The final position of the projectile is going to be at the water. So 0 meters is the final position of the projectile. What about the initial velocity in the y direction? The initial velocity in the y direction, we just found that. It's 125 meters per second. That was one of our answers for the previous question. The acceleration in the y direction is the acceleration due to gravity, negative 9.8 meters per second squared. And let's see, we are trying to find out how long the projectile is in the air. That is a question of the time. How much time is the projectile in the air? Okay, so for this problem, let's see, we've got initial and final positions in y. Initial and final positions in y. We have the initial velocity in y. Initial velocity in y. The acceleration in y we know, because it's the acceleration due to gravity, and we're looking for time. So it looks like the second equation is going to be the most appropriate to solve this problem. So let's go ahead and write down the second equation. Y final equals y initial plus v initial in y times time plus 1/2 times the acceleration in y times t squared. So substituting in our given information, we've got 0 for the final position, 50 for the initial position, plus 125 for the initial velocity in y, plus 1/2 times negative 9.8 times t squared. Let's go ahead and clean this up a little bit so that we can get to work. So 0 equals 50 plus 125t. 1/2 times negative 9.8 is going to be negative 4.9 t squared. Okay, so now we have a quadratic equation that we're going to have to solve for time. So in order to do that, we should either solve by graphing. So if you have access to like a graphing calculator like Desmos, so you could go to desmos.com and solve this by graphing. Or if you're like me and you don't have a graphing calculator on hand, then we should use the quadratic formula. So the quadratic formula, if you remember, says that this variable that we're solving for, in this case t, is going to be equal to negative b plus or minus the square root of b squared minus 4ac divided by 2 times a. So this is from your math class, if you remember, right? Very famous. This is the quadratic formula for solving quadratics. Let's go ahead and substitute in values. So this is c, the constant term. This is b, the 125 is b, the term in front of the t. And then a is going to be the term in front of the t squared. Let me circle these so that we can see that there's, I don't know, they're separate. Okay, so a, b, and c. Let's go ahead and substitute those into the quadratic formula. This is a little tedious, but we can do it. We'll just take a deep breaths. All right, so negative b is 125, plus or minus the square root of 125 squared minus 4 times a. A is negative 4.9. The negative is important. And then c is our constant term 50. So that's everything inside of the square root. And now we have to divide this by 2 times a. A, we said, is negative 4.9. Okay. So now we should put this in the calculator. I'll simplify a little bit for us. So negative 125 plus or minus the square root of, let's go ahead and put these things in the calculator. 125 squared is 15625 plus, let's multiply all these things together. So negative 4 times negative 4.9 times 50. This comes out to 980. And then we're going to have to divide this by 2 times negative 4.9, that's negative 9.8. Negative 125 plus or minus the square root of 16605, that's this 15,625 plus 980 comes out to 16,605 divided by negative 9.8. Okay, so we're going to have 2 roots, a positive one and a negative one, and the positive one is the one that we're interested in. Okay, fast forward, I wrote it out twice, right? One with the plus and one with the minus here for the plus or minus in front of the square root. And I put it in the calculator, and I got negative 0.39 seconds for one of the roots, and for the other root I got 25.9 seconds. So the negative answer, this negative time, doesn't have a physical significance for us. The positive solution to this problem is physically significant. This is the time that it's going to take the cannonball to go out of the cannon and then up in the air and then back down towards the water. So it's going to be in the air for a full 26 seconds, which is pretty impressive. And this is our solution for how long is the cannonball in the air. This would have been a lot faster if we had gone and done this using a graphing calculator. So we would have had to put into the graphing calculator y equals 50 plus 125t minus 4.9 t squared, and then find out where the function or graph, right, that's going to look like a parabola. In the graphing calculator, you're going to get something like this, and a parabola that looks something like this. And one of the places where the parabola crosses the x-axis, which in this case would be the t-axis, right, because we're dealing with time as our horizontal variable here and y as the vertical. So one of the places, one of the solutions here, one of the values of t that will make y equal to 0 is negative 0.4, and the other one is positive 25.9, and this one, positive 25.9 seconds is our solution that we're interested in here for this problem. So, by the way, yeah, if you have questions about this, right, try it yourself. Go to Desmos, go to the graphing calculator, put in this function into the graphing calculator, and take a look. These are the solutions. So you can either use the quadratic formula, which is a little lengthy, or you can graph it and see where the function crosses the horizontal axis of your graph, and that's going to be the solutions, the values of t, the values of time, that make y equal to 0, so where the cannonball is at the water level. Okay, so question 2 was probably kind of like the most challenging part of this problem, or at least like the most tedious, maybe not so much challenging, but just a little tedious having to use the quadratic formula. Now for the third question, I want to know how far from the cliff does the projectile land? So now, how far from the cliff? This sounds like a question about the x motion, the motion in the x direction. So I want to know, what is the displacement, what is the horizontal displacement of the projectile after it's fired from the cliff? So now we have some additional information that we got after solving question 2, how long is the projectile in the air? So let's write down everything we know about the motion in the x direction. We know that the velocity in the x direction is equal to, well, if you remember, question 1 we answered that the velocity in the x direction is 217 meters per second, and that stays constant. Whatever it was at the beginning, it's going to continue with the same speed in the x direction. So 217 is our velocity in the x direction. Then how far from the cliff does the projectile land? That's a question about the horizontal displacement. And the time that the projectile is in the air, delta t, we just found is 25.3 25.9 seconds. Okay, in the x direction we only have one formula because it's constant velocity of motion. So the formula is Vx. The speed is the distance over the time, so the displacement delta x over the time delta t. Let's substitute in values. The velocity in the x direction is 217 meters per second. The displacement we don't know, so we're just going to leave it as delta x. The time is 25.9 seconds. 25.9, so let's solve for delta x by multiplying both sides of the equation by 25.9. .9 times 217 is going to be our answer, delta x. So put it in the calculator. And the answer here is 5,620 meters, or about 5.5 kilometers. Okay, so that's a powerful cannon. Okay, great job, everybody.